So we are going to start with rotation. The main idea that we are going to discuss today, which is in the basic idea behind rotation, is the idea of what is angular velocity, what is angular acceleration. Okay, so these are two critical things that we have to understand here. In general, there are three quantities that we need to really understand deeply. You're going to use it everywhere in rotation. The first one is to understand what angular quantities are. And from angular quantities, we should be able to derive something that we call linear quantities. Now, you are already used to linear quantities. That's what we are using. When you talk about velocity, so far whatever we talk about as velocity, suppose I say I have this ball thrown with a velocity of 5 meters per second, that is linear velocity. Now, circular motion is very different from rotation. In circular motion, we do have linear velocity. The object going in a circle has linear velocity. We also talk about omega, but that omega is a little different from this omega. We will discuss that in more detail. The two other things that we have to understand to calculate quite carefully is torque, and a third quantity that we are going to call moment of inertia. Now, in linear motion, what we have done so far, every chapter that you have ever covered so far is all particle dynamics. Particles, only particles. Okay. So, for example, we learnt about 1D motion, we learnt projectile motion, 2D motion, circular motion, all of that. Then we also looked at Newton's laws. We looked at work energy and a little bit of momentum, not much, but if you add all that up, all of this we are going to repeat again, except that now it will no longer be for a particle. All of this was done for a particle. In this one single chapter, we are going to redo everything, but it will be for a larger object. Okay, and for a larger object, when you are studying Newton's laws, basically the main thing you are looking at is forces. Torque is going to be the equivalent for forces. Mass, you never actually have to calculate mass. For most questions, like mass of this thing is given to you, right? But here, obviously you have to calculate this quantity, which will be like mass. Force is usually given to you, but you will have to calculate the torque. So, if you know these two, then it slowly starts to look like what we have learned. So, these are two things that we are going to spend a lot of time, not today's class, but we will do a lot of work there. And the more important thing, or the starting point for all of this, is the fact that there are things that are angular quantities. We will study, first we will start with something that we call fixed axis. Okay? Then we will look at rotation in a general case. Many times people call it rotation plus translation, because rotation plus translation is the general case. Okay? So you can call it general case or rotation plus translation. So you will see that there is some very interesting stuff here, particularly when we get there we will look at it, that when you look at angular quantities, it turns out that it's actually a very, very simple idea. Okay, and that's the main idea that today we have to focus on, but that we will come to a little later. Let us start first with fixed axis objects. Before we start, all of what we are going to do, we are going to assume rigid bodies. We won't say it every time, but we will just assume that that's what we are dealing with, and it makes a big difference. If I took this duster and I throw this duster up, this duster goes up and comes back. Do you think it's translating? Yes. But it's only translating? Okay. So it is actually doing something that is reasonably complex. Looking at this motion, suppose this duster just went up and came back, right? Or even if this duster decides to go like that. Now all of that is translation. Why is this translation? All the particles are moving together in the same way. Okay. So if this object starts to move like this, I don't have to go in a straight line. It can be curved translation. When we talk about projectile motion, In that motion we are talking about a particle. If you take a particle cannot do anything except translate. If you take this particle, it can go from place to place. Why can't a particle rotate? Well, if you thought of a particle like a ball, it can rotate. Okay, that's because it has this side and that side. But this is not a particle, no? Particle is really small, it's a dot. It doesn't have any sides. So what do you mean by a rotation? Something must change. If the particle rotates, it looks the same exactly. So there is no measurement of a particle rotating. So particles can't rotate. So particles can only translate. So that's why we studied only translation, all of this situation. But if I take an object like this thing can translate. This is nice straight translation and this is curved translation. Okay, so tell me, what is this? Is that translation or rotation? Translation. It is translation. So if it goes like this, that is still translation. Because this object, this guy went in a circle like that, and this fellow goes in a circle like this. The circles are equal, the displacements are equal, they are not parallel. Okay, they are crisscrossing. The paths are not parallel. If they are straight, of course the paths will be parallel. It need not be parallel, but the displacements are equal. This is translation. Every point on the body moves the exact same way, which means I can talk about the acceleration of the body. For when you are doing Newton's laws, F equals ma, you are saying F on the body equals mass into acceleration of the body. But if each point has a different acceleration, then which point will you take? You can say center of mass, but that's not good enough. But if every point has the same acceleration, it doesn't matter. That's why when we did particle dynamics, we also did big blocks. But we treated the block like a particle. What does it mean a big block is like a particle? Every point moves the same way. That means the big body is translating. If I walk like this, at least the upper part of my body, well, not when I'm moving my hand, but the upper part of my body, you can think of as moving in translation, but not my lower part, right? And if I keep walking like this, then clearly I'm not translating because my hands are moving differently from my stomach, right? So therefore, particles can only translate. Bigger objects can do many very messy things, right? Now if I take something like this can actually not just turn around and walk around like this or move around like that. It can also compress, it can do all that stuff. And some of those things can come out, right? The powder can come out. But if I took something like this, it turns out this is reasonably simple. This cannot do too many things. It can't do the kind of things that this type of a sponge duster can. Whereas this fellow can go around, that is translation, that is like a particle. But this guy can also go around like this, right? If this one went from here to there, this point went like this point went like this. Different displacements, different paths. Everything has different paths here, but the displacements are clearly different. The magnitudes are different, direction is different. Okay, so we can think of this motion as two parts. 1, 2. Now that would be translation, that would be rotation, and that's why we study rotation first, and then we say anything else which is more complex like this is a combination of translation and rotation. So you want to study this, no problem, study this and then do all that. Okay, obviously that's not completely correct. You should have done it at step-by-step process, but instantly, at every instant, you can think of it as a combination of translation plus rotation. I can't say that I'll move all over the place and then rotate and dance it there, right? So, but you get the basic idea that you can treat it as a combination of translation plus rotation at every instant by instant. So, that's why we are going to right now first focus on just the rotation part. You already know a little bit about translation, then we will try and combine. So is that first clear? So before that, what did this thing involve that this thing does not involve? What is the speciality of this? What did it do? I know it rotated, but what did it do when it rotated? What is different direction? Different points move differently. Okay, that's the first part. Okay, then the orientation of the body changed. Here, the orientation did not change. The way it looks has not changed. Its position has changed. But if only position changes, then it is translation. If position and orientation changes, then it could be translation plus rotation. Right? Suppose the position, one point remains here, its position does not change, but the orientation changes, then it is rotation about a fixed axis. So is that idea first clear? If there is a point which is not changing its position, now the whole object you can't say is not changing its position, because different points are. Now let us say one point is not changing its position, but the others are. That means it is changing its orientation, right? And if it's changing its orientation, it is rotating. But that one point is not moving. So we can then call that point as the fixed point. And so we will talk of this kind of motion as the fixed axis rotation. Okay? So this is what we are right now going to focus on. It's a simple idea. But the key reason that we study this right now instead of studying something like this is because this guy can't do very much. Whereas this one can do this, and then in addition this alone can do that. So these 2 points, the distance between them is not fixed, not constant. Whereas here this point and that point won't get closer. If I throw it, it can rotate, it can do all that, it can move around, it can bounce, it can do all that, but this and this, the distance will remain the same. Studying a single point requires 3 coordinates: x1, y1, z1. If you are doing that on a plane, it requires 2 coordinates: x1, y1. Now if I want to study better than 1 point, I should study 2 points. So 2 points requires how many coordinates? 6 coordinates. So if I had 2 points, I am going to end up with 6 coordinates. Now a rigid body you may think is actually very complex because it has lots of points. But it turns out a rigid body is simpler than 2 points. Why is it simpler than 2 points? Because once I fix this point and that point, there is a condition in extra, which is that the distance remains constant. So 2 points with a distance remaining constant means if I fix x2 and y2, z2 is fixed. Because there is a connection that you can't just say this point, where by the time this one moves, this point has moved there and this point has moved here, so the distance has increased. This is not rigid. Rigid basically means that all the lengths everywhere the position is the distances are all the same. The positions are not the same, but the distances are all the same of all the points on the body. In which case this distance must be fixed. But if this distance is fixed, there is a condition: x2 minus x1 square plus y2 minus y1 square plus z2 minus z1 square is this d square, which basically means that one equation, which is effectively saying instead of 6 variables, how many variables do I have? 5. A general case rigid body has 5 variables. Okay. Now that is the general case. Now suppose I am talking about on a plane, generally I will need for two variables for 1 point. So I should generally have 4 variables. But it turns out that if I had this object, let's call it a planar object, and it was doing all that dancing around, very messy kind of thing. Okay. So let us say it did all that. Now when you do all that, you have to describe this guy's position, but you have so many points to describe. Correct, we may have a billion points to describe, but actually all you need to do is to think about one point here and some other point there. This point is somewhere which is x1 comma y1, and then you have to talk about one more variable which is angle. Done. Because once I know this is A, let's say that is B, once I know that B is like this at this angle, this entire rigid body has to be like that, fixed. So how many variables do I need? 3. I don't have 4 variables, I have 3 variables. How many points do I have? Billions. But billions of points you can describe with just 3 variables, because it's a rigid body. Now if I had a non-rigid body, very messy, because this guy can go all over. Well, it can't run away, but it can get closer. And that point can get closer differently. So not only can it rotate, not only can it translate, it can also move around. Then we need too many variables. Better than this is to talk about 2 variables. But better than this is to talk about 2 particles. Rigid body is easier than throwing these 2 balls. You may not agree, and it's correct. It has more variables if I throw these 2 balls to track them. But that's because this is independent of that. Right? Whereas a rigid body is not really independent, so it looks a little harder. But solving 2 linear equations in one variable is obviously very simple. Solving 10 of them is also quite simple. Suppose I say 3x is equal to 5, 4x is equal to 7. How easy is it to solve? 10 such problems, very simple. But if I had 2 variables that are connected together, then of course I will now need 2 equations to solve. Now that is more difficult than solving 5 of one variable equation. Now if I have 4 variables, I will need 4 equations to solve. But even if you look at 4 equations to solve 4 variables, it is better to solve 20 single variable equations. That is easier than doing this, right? The moment you connect, the mess increases. So if I tell you between this particle and this particle there is a force connecting them, it becomes very messy. But all things are like that. If you take the earth and the sun, one of the ways we study earth and the sun is to say sun is fixed, earth goes around. But sun is so heavy that it is fixed, or so massive that we just assume that it doesn't move. But in reality it does move. If you had earth and let's say you had something like Venus, which are almost similar sizes. Now you let these 2 fellows roam around. It is not like earth will go around Venus or Venus will go around earth. What will happen is this will start going around, that will also start going around, and it's quite a complicated thing to calculate. Just 2 particles, very difficult to calculate. Okay. The reason we study rigid body is also that it is the next hardest thing from a single particle. And it is easier than 2 particles. Okay. This is the easiest complex thing we can study. Okay. So we are going to spend a little time starting with why we are studying about rigid bodies, but I am not going to explain this anymore. Okay. What we are going to do is to assume now everything that we are dealing with is rigid body. With particles you have already dealt with circular motion, but this is a body, large body. Okay. So it's a little different. We will use some of the ideas we used in circular motion, but particles in circular motion is not the same as rotation. That is just simple circular translation. Can a rigid body also do circular translation? Yes. Okay, can it do curved translation? Yes. Can it do straight translation? Yeah, obviously. Can it, in addition to do this, do something else? Yeah, because it can do this and turn around, right? So that's basically what we are going to study. That is rotation plus translation. We will come to that very shortly. Right now, let us focus on fixed axis rotation.